Hello, my name is Scott Clark. Welcome to the SigOpt Summit. I'm super excited to talk to you today about intelligent experimentation and how it can help transform the way that you do modeling. I'm going to start out talking about the background that's led me to be in front of you today. I'm going to talk about where SigOpt sits within the modeling hierarchy and workflow. I'm going to talk a little bit about what intelligent experimentation actually is and go through all the various aspects of it, different trade-offs and things to think about when doing intelligent experimentation. And then I'm going to end with a few high-level examples and then a demo so you can get started with intelligent experimentation for free today. So first up, I'd like to tell you a little bit about how I came to be talking to you today. So I'm the founder and former CEO of SigOpt. We were acquired by Intel about a year ago. But my journey with intelligent experimentation really started about a decade ago when I was doing my PhD at Cornell in applied math. I kept coming into the exact same problem over and over again. I would build something really cool with my advisor or a collaborator in a national lab or another university. We'd apply a lot of domain expertise to build a new model, a new way of doing bioinformatics, whatever it may be. And at the end of the process, there was always this experimentation phase where we would tune and tweak all the various knobs and levers within these systems that we had in order to get slightly better performance, however that was defined for our project. If we could do it well, that meant a slightly better paper or a slightly better conference. We jokingly called this within my department grad student descent because it often fell upon the grad student to do this high dimensional optimization, oftentimes by trial and error in their head. This was an incredibly huge waste of both human resources, grad students, albeit cheap resources in the research community, but also computational resources. I wasted many thousands and tens of thousands of government supercomputer time, trial and error, tuning and tweaking these various models that we had built. So as a mathematician is wont to do, I was like, there's got to be a better way. And it turns out there is. And that's really the crux of the field of Bayesian optimization and global optimization more generally. I took some of that research, and when I went to Yelp after grad school, I literally saw the exact same problem. There, they had search systems or advertising systems or spam detection systems. Again, great complex algorithms that had been built up by domain experts that had lots of tunable knobs and levers that could make them more powerful, more profitable, or more accurate. The big difference here was instead of getting a slightly better paper if you did this right, at Yelp and in industry more broadly, if you could do this right, a whole bunch of money came out the other end. And that was really the crux for open sourcing Mo, or the metric optimization engine, one of the first application-based Bayesian optimization packages that's still being used worldwide today. And really why we formed SigOpt, because we realized that this was a problem that was pervasive across many different industries, many of which you'll be seeing here today in the summit. But it was also a problem that really needed to be solved with proper tooling, with a proper product. It wasn't enough to have cool math. You needed a way to apply this to your problems and do so in a way that allowed you to get more out of what you were trying to do. And that's really the crux of intelligent experimentation. So over the last 7 years, we've had the fortune of building up a great product, a great team, working with experts from around the world, many of which you'll hear from today, and really bringing the concept of intelligent experimentation to life. So I'm going to take a step back for a second and talk a little bit about where SigOpt sits within the entire modeling workflow and where intelligent experimentation sits. So a slide like this probably looks familiar. There's many different variations of this. It's basically the multi-scale fractal nature of modeling, of all the different components that go into it, all the different tasks and jobs that need to be done. I'm going to focus on this section right up here, where you're tuning hyperparameters, experimenting with topologies, doing some data augmentation, et cetera. This is where a lot of the tunable knobs and levers within modeling and machine learning exist today. Well, whether they be kind of more standard hyperparameters like learning rates or stochastic gradient descent parameters, whether they be architecture parameters like the topologies of a neural network, or whether they be the way that you're augmenting text, vision, or audio data before it's even fed into the machine learning algorithm itself. So within this subsection of the machine learning stack, there's quite a bit of things going on. Like everything related to modeling, it's a very nonlinear process. And modeling itself is a very scientific process. It differs from traditional software engineering insofar as there's quite a bit of experimentation that goes into it. A lot of hypothesis testing. Does this data set work? Does this model work? Is this problem even solvable? Is there a better way to do this, et cetera? As well as more applied optimization. Once I have something that works pretty well, can I make it better? What's the best I can make something? What are the possible trade-offs I could make before I go and put something into production? All of this experimentation is happening throughout the model building process. And it's inherently nonlinear, and it's a huge part of the time required to build models. As you'll see here, people call it different things, whether it's model tuning, model building, or explicitly experimentation. But this is often one of the largest parts of time required in order to get a model into production. And a huge chunk of a machine learning engineer, data scientist, researcher, whatever you call it, time as they're actually building models. And we like to break this problem into three chunks. And I'll go into much more detail on this as I talk about the aspects of intelligent experimentation. But at the very highest level, intelligent experimentation is about designing experiments, so asking the right questions, exploring experiments, so gaining understanding from the questions that you've already asked, and optimizing experiments. So once you've asked a good question, once you've gained understanding to make sure it's the right question, how do you get to the right answer as effectively and efficiently as possible? And SigOpt is about helping you along this journey, this nonlinear journey itself, to go back and learn, to ask different questions, to really open up the scope of questions that you can ask, and then again, to get you to that answer as efficiently as possible, both in terms of your time as the expert, but also in terms of computational time and the wall clock time required to get these models out. So as an intelligent experimentation platform, it fits within the modeling stack in that part of the journey. But in terms of actually fitting within your modeling stack, it really just bolts on top of whatever you're doing today. So you have a training environment that has your model and your data, et cetera. SigOpt represents a set of tools, a dashboard for managing, analyzing, and transparently sharing this experiment, an optimization framework for helping you get to the best possible version of these models, whether you're using our proprietary ensemble of optimization methods or bringing your own optimizer into our intelligent experimentation platform. And finally, an API to be able to do this scalably for the full volume, variety, and complexity of the models that you're dealing with day to day, handling up to 1 million API requests an hour for our customers, again, around the world. And each one of these customers has a slightly different problem, whether it's a different data set, a different modeling approach, different time constraints, different metrics, et cetera. This is just a small subset of the people who have been using SigOpt for the last 7+ years that we've been in business. And again, you'll hear a lot about them later today and their stories and experimentation and how they utilize intelligent experimentation to get significantly better results in their problem. So that's SigOpt, what we do and where we fit within the larger modeling stack. Now I'm going to take another step back and just talk about what is intelligent experimentation more broadly. So people, again, call it many different things. The experimentation bucket includes things from even just defining metrics, so understanding even the types of questions you can ask and what you want to shoot for, to doing the analyzation of the parameter space and really gaining understanding, to comparing different things, to tuning different things, stitching tooling together. There's many different things that people call this, many different ways that people are doing this. But I guarantee if you're building models today, you're doing experimentation today. But fundamentally, Again, this is a relatively simple concept, and the scientific method is built upon experimentation. Fundamentally, the difference between traditional experimentation and intelligent experimentation is this. Intelligent experimentation is designed to make recommendations and help you make design decisions, help you explore, and ultimately recommend optimal solutions. So instead of a system of record that just blindly records what you're doing, or an optimization method that you have no introspection into that's just blindly telling you what to do, intelligent experimentation is about having a collaborator, having something that learns as you're going, suggests as you're going, adapts as you're going, and ultimately helps you not only stand on your own shoulders as you're achieving new results, but standing on the shoulders of other giants as well to really accelerate this process of modeling and experimentation. And again, we think about this in three large buckets. And I'll go into more detail about some of the decisions, trade-offs, and aspects of each of these pillars of experimentation one by one. But the first is designing experiments. So this is, again, asking the right questions. And this is actually a very difficult problem. Naively, you might say, well, I'm doing a machine learning model, so I just want the model with the highest accuracy. But if you're doing a real world application, you might want to trade off that accuracy for inference time. And maybe it's not actually accuracy you care about. Maybe it's some complex combination of precision and recall. Maybe it's not actually quite just that, but there's specific subclasses that you need a threshold on to make sure you don't drop below a certain accuracy. But then you want the larger profit to be expanded, all while, again, keeping maybe inference time or memory footprint within a specific size so that you can actually deploy this in production. And all of a sudden, a simple question of like, I just want the best model, what's the best model, becomes this much more complex problem. But even designing the right questions to ask is a big part of this process. Exploration is about understanding, and better understanding leads to better questions that you can ask, but it requires you to keep track of everything, be able to analyze everything, see trade-offs, patterns, and ultimately take that experimentation, that high dimensional optimization out of your head and into a tool that allows you to get the most out of every hour you've spent and the cluster is spent to get these results and really get you to the best possible next step. Finally, optimization is about once you've phrased a problem in a specific way, how do you get to the best version of your model that satisfies that problem as efficiently as possible? So in as few computational cycles, as few back and forth trips, as few different configurations tried, you want to maximize a few metrics, have constraints on a few metrics, thresholds on a few metrics, et cetera, and ultimately get to a model or a collection of models that you can then put into production. So first up, I'm going to dive into designing. So there's a lot of different things that go into designing models and designing the questions that we can ask with an intelligent experimentation platform. So first up, the bread and butter of any modeling endeavor is the data itself. The data can have many different sources, versions. There's different ways to clean data. There's different ways to do feature engineering or augmentation. You're very often not just going to take a fresh data set out of a data lake and immediately throw it into a model, especially as these data sets get more complex around computer vision, natural language processing, audio, et cetera. And you'll hear some of this later today. Even the way that you're just instrumenting, augmenting, flipping, rotating, changing the color of, et cetera, the data itself can have a massive impact, not only on how long it takes to train, but ultimately how accurate your models are at the end of the day. The second thing that you need to choose when you're modeling is what model itself do you use? What frameworks are you using? Are you using deep learning, traditional machine learning, reinforcement learning, an ensemble method, some custom variation of these? Each one of the frameworks themselves have different trade-offs. PyTorch might be better than TensorFlow in certain applications, et cetera. So choosing the model itself is kind of a meta choice and can help phrase the design aspect of these models inherently itself. Once you've even chosen a model, there's still the choice to be made of what exactly am I having this model do? So how am I even having this model learn? Like, what is it learning towards with the data itself? What's the loss function? Is it trying to, again, maximize accuracy? Is there some L2 loss that you're trying to go for? Is there different ways that you want to parameterize how it's even going about justifying what success is and what it's trying to learn towards? Again, these loss functions themselves can have their own tunable parameters, and this can have an ultimate effect on whatever it is the production metric you care about might actually come out to be. So, how do you decide what's the best possible thing to do a priori? Well, you don't. You're never going to get this decision right perfectly the first time. So instead, what you should do is try a variety of things, but track everything. And again, in an intelligent experimentation platform, it gives you the ability to understand these trade-offs, analyze their differences, and ultimately get to that next stage of exploring the underlying models themselves. But just with a few lines of code in SigOpt, what you're able to do is start instrumenting and tracking all of these design decisions as you're making them. So you don't have to go back and say, wait a minute, that random forest that I used way back when, that actually had a pretty decent accuracy. Even after I've tried all this deep learning stuff, maybe I should go back there and do some tuning and tweaking, et cetera. Keep track of everything, have it in one place, make those decisions from an informed position. Exploration is really about, as you've got a model that works, as you've done this kind of initial smoke testing, hypothesis testing of like, can I get anything to work? Now it's all about like, what do I really want out of the system? How do I take the learnings from all of these individual models that I've run and really understand not just the loss function, what the model's trying to do, but what am I trying to do as a modeler for the business? And there's, again, many different metrics that go into this. And the lesson to take away from this section is track all of them so that you can understand which ones you want to optimize, which ones you want to maximize, minimize, which ones you want to put thresholds on, constraints on, which ones don't matter, etc. But ultimately, every metric goes through a life cycle. As you design it, you might discuss it with other people on your team. You might need to validate it against a simple data set and see whether or not it's even faithful to what you're trying to do. You might run experiments to test its precision. And then ultimately, you want to see how it works in the real world and what happens if you're overfitting it or if there's diminishing results, et cetera. So there's many different types of metrics that go into a machine learning problem, including training metrics. Again, this is what the model itself is training in order to try to achieve, whether it's a simple L2 loss or some sort of binary classification, whatever it may be. This is how the goalpost that you're giving the model before the data is even piped in. Tracking these is incredibly important, especially as you're doing the training itself, because this can help showcase maybe the brittleness of a specific model. If it just jumps up to a higher accuracy at a certain epoch, that might not actually constitute an interesting model. It might just be a very lucky stochastic gradient descent, unstable equilibrium. So understanding how these things evolve over time, how different trade-offs that are made, et cetera, is often an incredibly important part of especially more complex modeling endeavors. Validation metrics are the metrics that you're typically not training the model for. So they're not necessarily what the model is shooting for, but maybe they're one step closer to what you actually care about in production. These metrics might not be continuous or differentiable or convex or easy to calculate. This might be something closer to how much profit am I expecting to get in algorithmic trading strategy or whatever it is. Not something that you can directly put into a deep learning model for it to do stochastic gradient descent on, but something that you actually want to calculate maybe in a simulation environment or whatever it may be based off of the signal that that deep learning model is supplying to your overall algorithmic trading strategy. Um, these validation metrics come in many different forms. They're often very complex. And these are often things that you're designing as an expert yourself and want to continue to design as you learn more about the model. So this iterative process of exploration to change the metrics is an incredibly important part of an intelligent experimentation process. Finally, guardrail metrics. We see this come up all the time in production use cases. Again, there might be certain things that you're trying to maximize or minimize. And then there's certain things that just need to be true. Um, a model needs to be a certain speed to meet an SLA, or it needs to be a certain memory size to fit on an edge device, or it needs to satisfy some audit constraint in order to satisfy bias or whatever it may be. There's many of these application-specific needs that you don't necessarily want to maximize for, but you do want to take into account and make sure as you're maximizing towards a business objective, that you're at least meeting these guardrail metrics. Because having the most accurate model in the world and then trying to put it on the device and learning, oh, whoops, I guess it doesn't fit, is a terrible place to be in as a model. Finally, really a big thing about SigOpt is that we provide a lot of advanced tooling to really take into account all of these different types of ways that you're doing optimization. It's much, much more than just, oh, I have a single output from this simple model, and all I want to do is just get to the highest value as easily as possible. Really being able to zoom in on these trade-offs, put these thresholds, explore the Pareto frontier, et cetera, is an incredibly important part of that process and that exploration pillar itself of intelligent experimentation. Production metrics are kind of the true measure of the modeling process. This is what the business cares about, the profit and loss. Did what you make actually make the business better? These are often things that you cannot test in silico. Being able to say ahead of time whether or not it's going to actually perform well against the real market, in a fraud use case or an adversarial environment or whatever it may be. But these are important metrics to track as you get that information. So you can keep track in a single place the design decisions you made when making the model, the metrics you chose to optimize for, and the metrics you chose to care about in the exploration phase, but also ultimately going back and assigning the production metrics that were observed in the real world. So you can go and cross-correlate that to some of these training metrics, validation metrics, et cetera, to then again, rephrase your metrics, rephrase your questions, and ultimately get to the right question to ask before you go into optimization itself. And having all of this in one place is the only way to do that. Keeping track of this in different systems, an online metric training source, doing some of it in your head, only checking the magic numbers into Git, et cetera, is not a way to do this in a repeatable and transparent fashion. The final pillar of intelligent experimentation is optimization itself. So really boosting model performance by taking the model and getting to its peak possible performance. So this is about taking what ultimately looks like a black box system. It's a system that has many different inputs, continuous integer or categorical parameters. Those inputs could have their own kind of hierarchical dependencies or constraints on them, and observing the outputs of a system, whether it's a simple random forest or gradient boosted machine, or some super complex deep learning or reinforcement learning algorithm, whether it's running on your laptop in a Jupyter notebook, or whether it's running on a Department of Energy supercomputer cluster. Really making sure that as you phrase that question, we're able to go through this optimization feedback loop as few times as possible in order to get to the best possible results. And Bayesian optimization at the super highest level intuitively is about making the trade-off of exploration. So learning more about the underlying model, learning how these input parameters affect the output metrics, and exploiting that information to get you to higher and better output metrics. It's a global optimization strategy because it trades both of these off. As you're exploring more, you're learning more about the underlying model and the response surface. As you're exploiting, you're getting better and better results. But it makes sense for the algorithm to go back and explore more after it's already resolved a local optima. There's nothing left to exploit after you've already gotten to some peak performance. And so the algorithms will naturally trade off to go explore and learn more, find other optima, resolve those, and go back and forth as efficiently as possible. I've already talked about this a bit in the exploration phase of this, but one thing that we've seen many, many different times, and if you take one takeaway from this talk, it's this: it's machine learning or modeling or whatever you're doing that involves experimentation never involves a single metric. There's very rarely in life is there one thing you actually care about at the expense of all else. And making sure that you think about all of the different trade-offs, whether it's time and complexity, whether it's expense and accuracy, whether it's bias, whatever it may be, taking all of that into account and making sure that you're making the best possible trade-off is incredibly important. So don't blindly optimize for a single metric. It's not about winning a very rarely is life just about winning a Kaggle competition. It's more often about making intelligent trade-offs. And so optimizing many metrics, putting constraints on many metrics, putting thresholds, having these guardrails is incredibly important. And one of the tenets of, and one of the core capabilities of the Bayesian optimization and global optimization ensemble that we've built within SigOpt. One thing that's important to note, though, that is important for really any intelligent optimization system is the ability to be flexible, though. So we have a great proprietary Bayesian optimization system that we've built. It's got many patents and papers and collaboration that we've done over the years built into it. But one size doesn't fit all. The no free lunch theorem says there's not one algorithm that can beat every other algorithm at every single task. And so being able to bring your own optimizer is an important part of this, being able to switch off between optimizers, being able to take a hand-tuned system that's really good at solving one specific problem, but leveraging that within the scale, transparency, management, and analytics of a large and robust intelligent experimentation platform is incredibly important. We're developing more and more of these all the time, but it works out of the gate in terms of bringing your own optimizer. Due to the length of this talk, I can't go into detail about all of the different aspects of the optimization framework. Several decades of engineering years have been poured into our optimization framework. Again, battle tested with real world applications. Again, many of which you'll see today. Very different than specific academic use cases, but really looking at what happens when you throw these optimization methods in the real world. What happens with outliers? What happens when things fail? What happens when you can break the problem into multiple tasks? All these sorts of things have really informed all of these different features that we built over the years, and really expands the differentiation between an intelligent optimization and an intelligent experimentation platform, and just plugging in a random open source iterator you found online into your production methodology. So again, there's three pillars to intelligent experimentation. Design, which is the series of decisions and how you're phrasing these questions from the very beginning. Exploration, which is about learning from those experiments, kind of gaining understanding about your model and using that to rephrase those questions, get a better idea of what actually matters for your model. And finally, optimization. Once you have a good idea of what it is you're trying to achieve, getting there in as little data scientist time, wall clock time, and computational time as possible. And then going back and doing all of this again, potentially. But doing that whole process as efficiently as you possibly can. So a couple of quick examples here. So Numenta is one of our great customers. They use SigOpt a lot in the design aspect of things. They were able to use us in an intelligent experimentation case to get a sparse, high accuracy version of ResNet. Here it was about making sure that you phrase that question well, because again, when you're tuning things like a sparse network and hyperparameters and things like that all simultaneously, um, you need to be able to keep track of all of the trade-offs that you're making in order to, again, phrase the question in such a way that the optimizer can do its job and ultimately lead to this novel result. Exploration, and I know you'll hear about this a little bit later as well too, is about once you have an extremely complex model like a graph neural network set up, there might be many, many different metrics that you care about at the end of the day. Different metrics in terms of size, complexity, different trade-offs of accuracy, et cetera. And so here it's about exploration really driving you to better understanding of an incredibly complex model, which then again ultimately opens up the door to allow you to start optimizing, which of course is the third pillar. This is an example from Two Sigma, one of our customers for many years, that has used us to optimize a wide variety, volume, and complexity of models within their algorithmic trading strategies and machine learning models over the years, getting significantly better results than different open source optimization methods out there, and doing so in a way that takes full advantage of their large computational resources, being able to do asynchronous optimization across up to 100 different nodes per experiment for each one of these models, and getting to the best possible result in an extremely adversarial environment of algorithmic trading. So we've talked a little bit about SigOpt and intelligent experimentation, the aspects of it, gave some high-level examples, but now I'm going to dive into a demo with just a few lines of code. You can be off to the races and doing intelligent experimentation yourself. Again, SigOpt is a free service. So if you just go to sigopt.com/sign up, you're able to start doing this right now and could probably be up and experimenting by the time I get done with this demo. But I'm going to walk through this really quickly. I'm going to take a super simple data set, super simple model, so that we focus more on the intelligent experimentation aspect of things as opposed to the model itself. So I'm going to take the breast cancer data set that's available in scikit-learn. I'm going to use the XGBoost classifier, one of the most popular frameworks in the world for doing kind of gradient boosted machines based classification. And we're going to end up trying to tune a method that maximizes the recall for each one of these labels for this kind of medical application. But first up, here is the entire model. And again, it grabs the data set from scikit-learn. It parameterizes it. You can see here at the very beginning, we're starting to track some of these design decisions that were being made, the data set, the model, et cetera. And then at the very bottom, we're tracking things like the various output metrics, averages and weighted averages of the various classes, their F1 scores, precision, recall, and support, et cetera. All of this being kind of piped up to SigOpt as we go. One thing I'll point out, though, here in the middle is this is a very typical example of what we've seen in the real world, where people will build the model and either not set these hyperparameters like number of estimators, max depth, learning rate, et cetera, and just take the defaults, or start tuning and tweaking these by hand. A lot of times the defaults in these machine learning frameworks are designed to make a specific example look good or maybe run fast, but might not actually be the best sets of parameters for your production application. So with one line of code, what we're going to do is we're going to kind of abstract away those constants, and we're going to start tracking them within SigOpt, in addition to some of these modeling decisions and the output metrics themselves. So we can still put in the defaults, as you can see here, the number of estimators, the max depth, et cetera. But now as we set those, instead of trying to manually tune this three-dimensional space in our head, each one of those outputs is going to be tracked by SigOpt. As we do this and maybe try a couple of different things to gain intuition, again, instead of trying to keep track of a dozen different metrics and the input parameters and things like that in our head, we can quickly go to the dashboard and start to see some patterns, start to see, okay, certain learning rates seem to have a specific impact. We get more support in certain areas, et cetera. But ultimately, we can start trying to say, of all the metrics that we care about, what's something that we want to start maybe optimizing towards? So we've gone through the design phase of selecting a model and we're tracking everything. Now in this exploration phase, we're really trying to find a good objective metric or maybe set of objective metrics that we want to optimize for. One thing we'll note with this, even these 6 runs that we did manually here, is we can see, we start to see a pretty big spread in terms of the accuracy itself. We see like a 90%, a 94%, et cetera. So again, while our main case was to maximize the recall of both of these classes, we might want to start thinking about accuracy as something that we care about as well. So with SigOpt, this now allows us to start phrasing the question, giving us something to optimize towards. So again, in a few lines of code here, we're telling SigOpt that we're creating an experiment. We're tuning these 3 parameters and giving it a range of some integers and some double precision parameters to tune for. And any transformations that you might have on these parameters themselves. We'll tell SigOpt about the metrics that we're optimizing for. Certain ones we will want to maximize, certain ones we want to minimize, certain ones we just want to store and keep track of, like these precision metrics. Certain ones like recall we want to explicitly optimize for. So you'll see we're optimizing across these 2 metrics. And certain ones we might just want to put a constraint on. So I talked about accuracy maybe being an important metric that we care about. So let's say we want the best recall we can across both classes, with a constraint being that we want the accuracy to be at least 95% for the entire model as well. And now we just go through this loop of creating the model in the exact same way that we would have done before. Only now it's just, while the experiment is not finished, we're pulling down suggestions, getting suggestions from the SigOpt software as a service interface, evaluating them, reporting back those metrics. And as we loop over this, we're able to very quickly get to a set of results that are very interesting. So jumping back to the dashboard here, we can see that there's a set of gray points along this Pareto frontier, this efficient trade-off between the recall of both sets. These gray points don't meet that 95% accuracy threshold. These blue points do, but aren't as good as these orange points, these Pareto optimal points that are the best we can do in any one metric without giving up performance in the other metric. And so now, with a few lines of code, taking it just from the simple scikit-learn example, we've started tracking everything. We've started exploring a bunch of different metrics. We've designed an optimization problem and solved it across 2 different output metrics and a threshold to find 2 different models that satisfy our business constraints and our accuracy constraints. And ultimately, we could push into production and see how well they did. And then as we're exploring this, again, there's many different ways to, after you've actually done the optimization, go back to exploration. Start looking at how all of these different metrics traded off with different parameters, and maybe gaining insights on how we might want to shrink down or change the learning rate and log space here, etc. This is not a linear process. What I'm showing you here in this demo is just one potential path. There's many different paths, but it ends up being a cyclic problem where you're constantly going back to ask different questions, explore different metrics, etc. So at the highest level, what this has allowed you to do with a few lines of code after a quick pip install SigOpt is design your experiments, explore your experiments, and ultimately optimize your experiments to hit your business needs. So that's SigOpt in a nutshell. Again, all of this is available for free today. If you go to sigopt.com/sign up, you can be up and optimizing by the time I'm done with my Q&A. And we look forward to helping you achieve the best possible results for your models, spending less time on trial and error and more time with a collaborative, intelligent experimentation platform. Thank you.